Hello everyone, welcome to Math 60. This video lecture is section 4.1, which is solving systems of equations graphically. So I want to remind you of what I've shown you a couple times, this idea that there are lots of different ways to represent mathematical ideas, and the four most common are symbols, words, numbers, and pictures, and how you can move from one to the other to help you understand the mathematical situation and maybe solve some questions. Solving systems of equations graphically usually involves moving from symbols down to pictures, in this case, graphs. Sometimes you start with a word question, and you may be able to go straight to graph, or maybe you go up through symbols and then down to graphs. But the idea in this section is really focusing on using our graphs to help us solve systems of equations. So first, let's talk about a system of equations. What that is a set of two or more equations that share variables, and therefore if there's a solution, the solution needs to work for every equation. If a system of equations has a solution, it means that the solution works for every equation. So let me give you some examples before we do this graphically. Here's a system of equations. X plus y equals 3 and x minus y equals 1. We usually denote that we have a system with this brace here, and that indicates if I'm looking for a solution, it has to solve both equations. And notice that if I choose x equals 2 and y equals 1, then 2 plus 1 equals 3, and 2 minus 1 equals 1. So my system of equations has a solution that involves an x and a y, since it's a variable that appears in both. And in order to solve, the x and the y have to solve both the first and the second equation. So let's look at what solving this system of equations might look like graphically. I was able to solve this one just by making a reasonable guess and checking it systematically. But I could also solve this by graphing each of these equations. Notice, since the equations have two variables, I can graph them in a coordinate plane or coordinate system. These equations are both written in standard form, which means I can do an x-intercept, y-intercept thing. For the first equation, if I let x equal 0, that means y would be 3. And if I let y equal 0, that means x would be 3. So my first equation looks like this. And my second equation, if I let y equal 0, x would be 1. And if I let x equal 0, negative y would be 1, so y would equal negative 1. And so I have something that looks like this. And notice that these two lines cross. And where they cross is the solution. Because the first line contains all xy pairs that solve the first equation. And the second line contains all xy pairs that solve the second equation. And the only point that's on both of those lines is the intersection. And the coordinates of that point, although my drawing wasn't great, the coordinates of this point are xy equals 2, 1, which is exactly what I found, x equals 2, y equals 1. Just about any system of equations can be solved graphically if there is a solution. You just look for any intersection points of the graphs. We're going to focus on linear equations, but they don't have to be. Here's some function that's nice and curvy, and here's another function that's nice and curvy. And I can solve the system of equations just by looking for where these two graphs intersect. Those two intersection points will be the two solutions for this system of equations. Let's do another example. Let's solve the system. Let's do x minus 2y equals 10 and y equals 3 times x minus 1 plus 2. And notice I have different forms of these linear equations. This first one is in standard form, and the second one is in point slope form, but it doesn't really matter because when you solve the system graphically, step one is just to graph the two or three or more equations. And I'm going to stop trying to graph by hand because Desmos does this very quickly and easily. So instead, let's go over Desmos and let's put our two equations in. X minus 2y equals 10. There's one equation. And the other one was y equals 3 times x minus 1, close it up, plus 2. And there's my intersection point. That's my solution. The solution to this system of equations is xy equals negative 1.6, negative 5.8. Xy equals negative 1.6, comma, negative 5.8. Those are, in fact, that's the only xy coordinate point that is on both of these lines. So it's the only xy pair that makes both equations true at the same time. And that's exactly what it means to be a solution. So step one, you graph it. Step two, look for any points of intersection. And step three, write the points as xy coordinates. Those are the solutions. Usually, almost always, you're going to find just a single coordinate point when you're working with linear equations. But as I said, this works for any equations. So when you have, for example, graphs that curve, you might have more than one point of intersection. All right, I said that most of the time we're going from symbols to graphs. So we have these symbols here, and then using Desmos, I graphed them, and one looked like this, and one looked like, sorry. Using Desmos, I graphed them. The first one looked something like that, and the second one looked something like this, and then that point of intersection right there, xy, was negative 1.6 comma negative 5.8. I'm fine with decimals. Desmos gives you decimals, but we're solving things graphically. So if that's what Desmos gives us, no problem. Going from symbols to graphs is how we normally do it, but sometimes we start with words. Let me give you a word equation that we're going to convert to symbols and then convert to a graph to solve it. Okay. Joe catches a pass 50 yards from the end zone. And runs at 5 yards per second. I don't know if that's fast or not. Feels fast to me. Toward the end zone. Fanny is 70 yards from the end zone and chases Joe at 8 yards per second. When will Fanny, or how far from the end zone? Yeah, when will Fanny catch Joe, and will it be before the end zone? All right, so here we have a word question, and solving this by graphing would probably be helpful or an easy way to do it, but in order to do that, we need to convert it into symbols so that we can put it in Desmos, for example. So let's do the Joe equation first. Joe, let's say y is the distance from the end zone, and x is time. And so Joe's distance from the end zone will be 50 yards, but minus 5 yards every second. And Fanny's distance from the end zone will be 70 yards minus 8 yards every second. And so here I have a system of two equations and two unknowns. And the time when they meet and the distance they will be are the xy that solve the equation. So if I solve this system, I find the time and distance when they meet. And so let's go over to Desmos and see what it looks like. I encourage you to use Desmos every single time when solving equations with graphing. On occasion, you may be asked to graph these equations by hand. You can use Desmos to help you, or you can practice doing it by hand. But let's see what we get when we go to Desmos. So one of our equations was y equals 50 minus 5x, and the other was y equals 70 minus 8x. Zoom out a little bit, and I can see that although Joe's getting closer to the end zone, Fanny looks to be catching up, and there's that intersection point. Desmos is pretty good. If you click somewhere, it'll show you the point, but usually the point doesn't stick around unless it's important. Like an x-intercept will stick around and a y-intercept will stick around. But if it's not an interesting point like an intersection, it won't stick around. So the solution to this system is xy equals, I think it was 6.667 and 16.667. Let me double check. Yep, more or less. I rounded it, but we're talking distance. And at a certain point, it doesn't matter if you're a tiny fraction of a yard. So to put it back in context, I would say it will take Fanny 6 seconds to catch Joe, and Fanny will catch Joe on the 16 yard line, right? So maybe 16.6 if I want to be precise, 16.6 seconds to catch Joe, and Fanny will catch Joe on the 16.6 yard line, or a little more, right? Which is before the end zone. So Fanny catches Joe before Joe scores a touchdown. I'll transcribe these over to the paper just so you have them in my paper notes. And also we can practice sketching these graphs by hand. So this is y and x. When y is 0, that's the end zone. All right, that is when the distance to the end zone is 0. So Joe is going to start here at 50 yards. And every second, Joe's going to run 5 yards closer. So I've changed my scale a little bit just to be able to draw it. That's why these lines look different than Desmos. I could keep drawing these lines, but let's keep in mind this is a real situation, and we're not counting before Joe caught the ball, and we're also not going to count once Joe gets to the end zone. So I can basically just draw the line segment that goes from here to here. It should take Joe 10 seconds, because 50 minus 10 times 5 is 0. 4, 5, 6. Okay, good. And then Fanny starts here at 70 and runs a distance of 8 yards every second, which is going to take Fanny just a little under 9 seconds to get down to 0. So it's going to be something sloped a little bit more like this. And then that point right there is the point 6.667, comma 16.667. Of course, it's not going to be perfect when I draw it freehand, but it definitely gives me an idea that Fanny will catch Joe. And this is the whole point of using graphing technology, is to be able to get precise answers even when we're using graphs instead of by hand. That's it. That is how you solve systems of equations by hand. Couple of other ideas. Nobody says you have to stop at 2 equations. You could have more than 2 equations. Usually, the number of equations matches the number of variables. If that is the case, then you can potentially solve your equation. So if I had, let's just look at an extreme example. Um, let's do a system of two variables, but just one equation. And we've done this before. This is like x plus y equals 3. Well, x could be 0 and y could be 3, or x could be 1 and y could be 2, or x could be 2 and y could be 1. There's infinite solutions here. So not super helpful. But as soon as you add in another equation, like x minus 1 equals, x minus y equals 1, now most of these possibilities won't work. 0 minus 3 does not equal 1. 1 minus 2 does not equal 1. But x equals 2 and y equals 1 does work. So if the number of equations matches the number of variables, you can usually find a unique solution. You could have 3 variables and 3 equations, or 10 variables and 10 equations. Nobody wants to solve 10 variables and 10 equations by hand, but there are also some nice numerical tools for solving that. Someday in a future class, you might learn about those. Usually you can solve, but sometimes two equations with two unknowns have 0 solutions. And this is easiest to see with a graph. Let's look at the system x plus y equals 3 and x plus y equals 4. Now you may notice right away that if x plus y equals 3, it's not possible for x plus y to equal 4. Right? 0 and 3 would work, but 0 plus 3 is never going to equal 4. 1 and 2 would work, but 1 plus 2 is never going to equal 4. So if we look at this visually, I'll draw this by hand, and let's use find the intercepts point. So if x equals 0 on the first one, y equals 3, right there. And if y equals 0 on the first one, x equals 3. This is one of the functions I used earlier. It's going to look like this. But now I go to my second equation. If x equals 0, y equals 4. And if y equals 0, x equals 4. And what I end up getting, if you think back to the previous section, are parallel lines. Parallel lines means no solutions to the system. That's because parallel lines never intersect. And as we saw earlier, the only solutions are intersection points. So if parallel lines never intersect, they never have solution. I'm sorry, if they never intersect, they never have intersection points. So they don't have any solutions. Another way to think about this is these two lines have the same slope, but different y-intercepts. That's another way to say that lines are parallel. If they have the same slope, then they must be parallel or overlapping. And then if they have a different y-intercept, they're not overlapping. Well, let me show you another example. This time I'm going to write it in slope-intercept form. Y equals 2x minus 3 and y equals 2x plus 1. So if I graph this, 2x minus 3 looks like that. And 2x plus 1 looks like that. And notice, since they have the same slope, they're parallel. Oh, since they have the same slope, they could either be parallel or overlapping. And since they have a different y-intercept, they're not overlapping. They're parallel, no solutions. And as you can imagine, putting your two equations and graphing them will show you immediately if they're parallel, in which case there are no solutions. And the last possibility is sometimes two equations with two variables have infinitely many solution pairs, infinitely many solutions. So let me give you an example. X plus y equals 2, and 3x plus 3y equals 6. Now, if x is 1 and y is 1, that works. And 1 plus 1 is 2. And in the second equation, I have 3 plus 3, which is 6. That works. And same if I take like -5 plus -5. Oh, excuse me. That's not what I meant. I meant something like 3 plus -1, that equals 2. And 3 times 3 plus 3 times -1 is 9 minus 3, which is 6. And that works also. So these two lines not only have the same slope, they also have the same y-intercept. If you were to graph, you'd see that in the first equation, if x is 0, y is 2. And if y is 0, x is 2. And in the second equation, if x is 0, 3y equals 6. But that also means that y is 2. And when y is 0, 3x equals 6. And that also means that x is 2. What that tells us is if I try to graph my first line, x plus y equals 2, and then I graph my second line, 3x plus 3y equals 6, it's going to be one right on top of each other. These lines are the same. And what that means is any xy pair that solves the first equation is also an xy pair that solves the second equation. Any xy that solves one equation also solves the other. And since it's a line, I have infinitely many xy pairs. There's an xy pair that solves. There's another one that solves. Here's another one that solves. The y-intercept and the x-intercepts both solve. I have infinitely many solutions to both of these equations. So these are the three possibilities. You could have, and most of the time you're going to have, because of the way the world works, you're going to have two lines that cross in one point, and it gives you exactly a single solution. Sometimes you could have two lines that are parallel, or they have the same slope but different y-intercepts. There will never be a solution. Or you can have two lines that look different, but they're actually the exact same, in which case you have infinite solutions. All right, that brings us to the end of this video. The next video will look at how do you solve systems of equations without graphing. Thanks for watching.